In section 8.4, we're adding and subtracting radical expressions. Our objectives are to simplify radical expressions involving addition and subtraction. Simplify radical expressions involving addition and subtraction. We can only combine radicals that have the same index and the same radicand. We consider them to be like terms. So what we have here is 1 square root of 6, we can think of it as a 1 in front, plus 5 square root of 6 plus 2 square root of 6. These are considered like terms since they all have the same index and the same radicand. So we consider them to be like terms and we can combine them into a single radical. So 1 square root of 6 plus 5 square root of 6 plus 2 square root of 6 is the same thing as 8 square root of 6. So again, we can only combine rational expressions if they have the same index and the same radicand. In the second example, we can combine like terms. The terms that are the same include the 3 square root of 5 along with the plus square root of 5. Those two are considered like terms, so we can combine those into a single radical. 3 radical 5 plus 1 radical 5 is 4 radical 5. We can also combine the terms that's plus 2 square root of 11 minus 5 square root of 11. Those are considered to be like terms since they have the same index and the same radicand. So we combine them to get plus 2 square root of 11 minus 5 square root of 11, which is minus 3 square root of 11. So our final answer ends up being a binomial. We have two terms in this radical expression, 4 square root of 5 minus 3 square root of 11. Now again, caution, only radical expressions with the same index and the same radicand may be combined. Expressions such as 5 square root of 3 plus 2 square root of 2 cannot be combined because they don't have the same radicand, as well as the expression 3 square root of 3 plus 2 cubed root of 3 cannot be combined because the indexes are different. Let's continue to work through adding and subtracting radical expressions. In example 1 on the left side here, we have the square root of 3 plus the square root of 27. These, as they're written, are not like terms, but if we simplify, we may be able to combine these into a single radical. Let's simplify the square root of 27. We know if we build a factor tree that 27 is the same thing as 9 times 3. And 9 as well can be written as 3 times 3 times 3. So the square root of 27 has a perfect square that can be simplified. And if we bring down that first term as a square root of 3, and the square root of 27 simplifies to 3 square root of 3, again that perfect square 3 times 3, the square root of 9, comes out as a single 3 in front of the radical. So we end up with 1 square root of 3 plus 3 square root of 3. That will simplify to 4 square root of 3. Let's look at the example on the right. The square root of 128 minus the square root of 32. Now 128 can be simplified by building a factor tree. The square root of 128 is the same thing as 2 times 64. Now 64 is a perfect square, so we can simplify this as 8 square root of 2. Otherwise, you can continue doing the factor tree to simplify the radical expression, the square root of 128, which is equivalent to 8 square root of 2. We can do the same thing with the square root of 32. The square root of 32 is the same thing as 2 times 16. And again, 16 is a perfect square, so we can take the square root of 16 and write this as 4 out in front of the square root of 2. And then our expression becomes 8 square root of 2 minus 4 square root of 2, and these are considered to be like terms because they have the same index and the same radicand. So we can simplify this by taking 8 minus 4, which is 4. So our answer is 4 square root of 2. Okay, for the example, on the top of this slide we have 3 times the square root of 8x squared y plus x times the square root of 2y cubed minus x times the square root of 50y. Let's see if we can simplify these radicals. As it's written, there are no like terms, but we can perhaps simplify. Notice that we have the 8 can be written as 4 times 2, and x squared, that's x, times y. So the 3, the fact that we have square root of 4, which is a perfect square, and x times x is a perfect square, we can write this as 3 times the square root of 4, which is 2. So that's 3 times 2, which is 6. X, the square root of x squared is x out in front. 6x times 2y under the radical. Now the second term, x times the square root of 2y cubed, the y can be factored. That's y times y times y, so we've got that pair of y's there that can be simplified. And we can bring that y out in front so that our second term simplified is xy times the square root of 2y. And our last term, minus x times the square root of 50y, can be simplified because the square root of 50 can be written as 25 times 2 times the y, and the 25 is a perfect square, so that can be simplified taken out in front, so that our last term is written as minus 5x because the square root of 25 is 5, and the square root of 2y left under the radical. Now we have 3 like terms. We say that they're like terms because they have the same index and the same radicand, the same index and radicand for all 3 of those terms. So we add the coefficients together. But notice that the coefficients have variables in them. So we need to be careful as we add the coefficients together, and we can write the result as 6x plus xy minus 5x, all of the coefficients combined together along with the square root of 2y. In the parentheses, we can simplify the 6x minus 5x and write this as x plus xy times the square root of 2y. So this is how we can write our final answer to the radical expression. And again, we were able to combine this into a single radical by simplifying each of the radicals and adding the results because they had the same index and the same radicand. Let's look at the example at the bottom of the page. We're looking at 10 times the cubed root of 16a to the 4th b squared plus 11a times the cubed root of 54ab squared. The 10 out in front, and when we simplify what's under the cubed root, we're looking for perfect cubes, and 16 can be written as 8 times 2, and a to the 4th can be written as a to the 3rd times a, and a b to the 2nd power. The perfect cubes that we have here are 8 and 8a cubed. The cubed root of 8 is 2, so we can bring that out in front of the radical, and a cubed, the cubed root of a cubed, is a, which can also be brought out in front of the radical. Now what we have left under the cubed root is going to be 2ab squared. Let's look at the second term here, plus 11a out in front, the cubed root of 54ab squared. 54 is the same thing as 2 times 27, and 27 is a perfect cube. So we can simplify the cubed root of 27, which is 3, and bring that out in front along with the 11a times 3, and then everything that's not part of a perfect cube is going to stay under the cubed root. So we end up with like terms. We can simplify the coefficients of those radicals So we get 10 times 2a, which is 20a, times the cubed root of 2ab squared, plus 11a times 3, which is 33a, times the cubed root of 2ab squared. Now do notice that we have like terms here. We have the same index and the same radicand, so we can add these together. And we have 20a of the first radical plus 33a of the same radical. So we can combine them to a single radical to get 20a plus 33a, or 53a, times the cubed root of 2ab squared. As our final answer. All right, let's simplify 3 times the square root of 72 over 25 plus 5 times the square root of 18 over 50. What I noticed right away is that under the square root on the right side here, 18 over 50, these are both even numbers. This fraction can be reduced. 2 goes into both of these. 2 goes into 18 9 times, and 2 goes into 50 25 times. So that's one thing that we can do. Now we can rewrite our expression as 3 times the square root of 72 over the square root of 25. I'm writing this as 2, the quotient of two radicals, plus 5 times the square root of 9 over the square root of 25. Now look that we can simplify many of these radicals. So we have 3 times the square root of 72. 72 is not a perfect square, but the square root of 25 is. So we can write this as 3 squared is 72 over 5, plus the second term, 5 times the square root of 9, is 5 times 3 over 25, the square root of 25, which is 5. And these two 5s can cancel out. Now let's look at the square root of 72. The square root of 72 can be written as 36 times 2 over 5 plus the second term of 3. Now notice that the square root of 36 is a perfect square, so we can write this as 3 times the square root of 36, which is 6. So the 6 goes out in front of the radical with the square root of 2 left underneath. And then we have divided by 5 plus 3. Let's simplify this one more step here, and we get 3 times 6, which is 18. 18 square root of 2 divided by 5 plus 3. On the right side, we have 12 times the cubed root of 7 over y to the 9th minus 7 times the cubed root of 11 over y to the 12th. Let's simplify the radical expressions. We can write this as 12 times the cubed root of 7 in the numerator and the cubed root of y to the 9th in the denominator, minus 7 times the cubed root of 11 in the numerator over the cubed root of y to the 12th in the denominator. Now 7 and 11, the radicands and the numerators, are both prime numbers, so they're not going to be able to be simplified. But the denominators can be simplified. We can write the first term as 12 times the cubed root of 7 over the cubed root of y to the 9th. Well, the cubed root of y to the 9th can be written as y to the 9th raised to the 1/3 power, and that can be simplified as well. So we can write this as 12 times the cubed root of 7 over y to the 9th to the 1/3. Using the power rule for exponents, when we have a power to a power, we multiply. So 9 times 1/3 is 3. So we can write this as y to the 3rd. Now the second term here, the numerator cannot be simplified, but that denominator, the cubed root of y to the 12th, we can write as y to the 12th raised to the 1/3 power. Using the power rule for exponents, when you have a power raised to a power, you multiply the exponents together. So our second term becomes 7 times the cubed root of 11, all divided by y to the 12th to the 1/3 power. Well, y to the 12th to the 1/3 power, 12 times 1 over 3 is 4. We can write it as y to the 4th power. Now we can leave our answer in this form, It is also possible to combine this by getting the least common denominator. The least common denominator in this case is represented by the denominators, the factors of all the given denominators, and that would be y to the fourth. So the first term is missing a y to the fourth. It has a y to the third. So to get a common denominator here, we could multiply the numerator and the denominator by y. With that result, we get 12 times the cubed root of 7 times y. Now it's preferable to write that in front of the radical so as not to confuse that it's underneath the radical sign. It's not, so we want to put that out in front. All over y to the fourth minus 7 times the cubed root of 11 over y to the fourth. Now we can write this as a single rational expression. Because we have a common denominator, we can add or subtract the numerators. So our first term, 12y times the cubed root of 7 minus 7 times the cubed root of 11 in the numerator, all over the common denominator of y to the fourth.